Conclusion: methanol from available fossil fuels will remain the major source for now. But the most important statement here is that the chemical reductive recycling of any carbon dioxide produced will become very important as we try to lower the carbon fingerprint in our atmosphere. This is ultimately the most important goal in my estimation. Microbial or photochemical methods. Certain bacteria, methanotrophs, have been known for quite a few decades, and they can exist on methane. Selective conversion to methanol using diatomic oxygen can be looked at here. Now, metabolism yields formaldehyde, which can be incorporated into biomass or oxidized to carbon dioxide, thereby generating chemical energy. The enzyme is methane monooxygenase, MMO, which can operate at ambient temperature and pressure in aqueous solution. The methane and reduced coenzyme NADH and hydrogen and oxygen yields methanol and oxidized coenzyme in water. Now, two forms of enzyme have been found for this interesting conversion. One, containing copper, is membrane-bound, and any membrane-bound enzyme is going to be difficult to isolate and characterize. Another, however, is soluble, and it contains iron. And here are two Methylocinus genus, two species known that have a soluble iron-containing enzyme for this process. The active site of the enzyme has two iron atoms, and efforts are being made to understand the active site chemistry and dynamics, so the possibility of synthesizing catalytic mimics can be considered. Now, Cytochrome P-450 has a porphyrin system, and porphyrins are known to oxidize a range of hydrocarbons, but methane cannot be reacted. Is it possible to genetically engineer the porphyrin system? In the long term, methanol production from biomass will minimize carbon footprint, but will be unable to cover all global needs. Since biomass is both bulky and heterogeneous, it would make sense to convert it to a liquid fuel such as methanol. Now, current technologies would convert it to syn-gas, such as what's done with feedstock coal. The biomass is first dried and pulverized with moisture content brought to a upper level of 20% and torrefied. Let's call it torrefied material, roasted material. Some of the mass is combusted to generate the temperatures for syn-gas formation, and the balance is treated with water and carbon dioxide, the combustion gases, to form carbon monoxide and hydrogen. Syn-gas. In actuality, syn-gas and biomass in one step has had technical difficulties. A two-step process has been developed. Pyrolysis first, destructive distillation. This generates charcoal, which we now call biochar, and you get producer's gas, which has been known for decades: carbon monoxide, hydrogen, methane, carbon dioxide, water, and volatile tars. We've done this in the laboratory, and you get this distillate or producer's gas, part of which can be condensed to biogas. The second step, the char conversion, the material is treated with oxygen at 13 to 1500 degrees Celsius, which produces carbon monoxide. This is syn-gas, which is cleaner than that from coal. The quantity of biomass needed for global methanol needs is quite large, 1.5 million tons annually. Biomass would have to be collected over vast areas of land and transportation. Low energy density long distances is not economical. Thus, fast pyrolysis is proposed. Small biomass particles are heated very rapidly to 400 to 600 degrees Celsius at atmospheric pressure to yield oxygenated CH gases. This in turn is rapidly quenched to avoid cracking, which in turn leads to decomposition. This resulting black liquid is called biocrude and can be used as fuel oil or possibly refined in conventional oil refineries along with petroleum. Biocrude is isolated in 70 to 80% yield. The production of syn-gas from biocrude is promising. The formation of biocrude is economical and can be transported readily. In Japan, the Mitsubishi Heavy Industries is operating a pilot plant to produce methanol from biomass. In the United States, the Heinol process, Brookhaven Labs, successfully converted wood chips to methanol. Black liquor, known to those in the paper-making industry, the Kraft process byproduct black liquor, is being converted to methanol in Europe. That's mostly sulfonated lignins, with some cellulose and free sugars. 65 to 75% of the biomass in black liquor can be converted to methanol. 170 million tons of black liquor is produced annually on a global basis. Plenty of it. Right now, most of the plant-making facilities burn it. They just use it as a fuel. The United States can produce 28 million tons of methanol this way, but our domestic use of gasoline diesel fuel is equivalent to 1,000 million tons of methanol. That must be kept in mind, that figure. Finland and Sweden can obtain 28 to 50% of their total transportation fuel needs via black liquor. The United States municipal solid waste, 240 million tons produced annually, is a potential feedstock for methanol production. Biomass. Fast-growing tree shrubs are currently being selected for raw biomass material. The potential impact of these tree shrubs on ecosystems, soil erosion, water quality, and wildlife is being assessed. Poplar, sycamore, willow, silver maple are being considered for the United States and Europe. Here on our campus, I am growing a couple of different species of willow, a fast-growing willow shrub, which is surprisingly drought tolerant. And it can be harvested every 2 years. It grows to about 20 feet and can grow right from the stumps, regenerate. A 4 to 10 year harvest of the above trees is being proposed. Switchgrass, sorghum, sweet sorghum is also being studied. A significant portion of idle food crop lands, pasture range, and forest land could be used for energy crops. Biomass, continued. Fertilizers have to be considered, and these nitrogen compounds are responsible for 65 to 80% of the total emissions of nitrous oxide, a greenhouse gas, which is 296 times more damaging than carbon dioxide. In the air. Global warming. In Australia, their National Science Agency devised a computer model to show that 30 million hectares of fast-growing planted trees over the next 50 years could produce enough methanol to replace 90% of the country's oil requirements by 2050. That's for 25 million people. A hectare is roughly 2.5 acres. Biomass in Europe is not expected to represent more than 10 to 15, that should be percent there, 10 to 15% of the total energy demand in the future. 400 million hectares in the European Union land area and 170 million are currently used for food production. 160 million are covered by forests. This is the conclusion of Part 2. I refer you to Part 3.